It's a hair past noon, so I'm going to go ahead and get us started off. First, by welcoming everyone to this webinar. My name is Beth Engum. I'm a Senior Transportation Project Manager at Bolton and Mink, and I'm also the Chair of the CTS Transportation Infrastructure Research Council, who's the sponsor for today's webinar. So a little bit of background for you folks about the councils. The CTS councils provide a forum for transportation professionals and researchers to exchange information on current transportation issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. Sam's going to share a link to the council's information in the chat shortly. Today's webinar will feature a presentation on infrastructure materials and performance. And I'll share more about that in a moment, but first I'd like to turn it over to our Council Vice Chair, Kristen Foster, who is co-facilitating this webinar. Kristen, you want to introduce yourself and cover some of the details?
Good afternoon, everyone. Thanks, Beth, and thank you all for being here today. I am the Planning Group Manager for Stonebrook Engineering and Vice Chair for the CTS Transportation Infrastructure Research Council. We're looking forward to audience participation and questions during the Q&A time, which follows the presentation. We encourage you to use that question and answer at the bottom of your screen anytime to type questions or comments for the speakers. And during the Q&A at the end, you could use the raise hand feature if you prefer, then we will unmute you to share verbally. We'll also be monitoring questions in the chat box as we go. Today's event meets the continuing education requirements for 1.5 PDHs and 1.5 AICP certification maintenance credits. If you need a PDH form, send a chat message to all panelists with your name and email, please. We will email the form to you following today's event. In addition to this afternoon's webinar, CTS will be holding 3 other transportation research webinars that you may be interested in. Coming up on April 22nd, Species from Feces, a new tool to identify bats in culverts and on bridges. The next day on the 23rd, EV infrastructure and fuel policy, understanding the transportation and economic impacts. And lastly, on May 19th, for our spring webinar series, is How Infrastructure Shapes Driver Behavior and Pedestrian Safety. Information on each of these webinars, along with registration information, is available on the CTS website at cts.umn.edu/events/seminars. Additionally, CTS will be hosting 2 in-person events on Tuesday, May 5th, at the McNamara Alumni Center on the University of Minnesota campus in Minneapolis. The All Councils meeting from 9 a.m. to 11:30 a.m., followed by the annual meeting and awards luncheon at Memorial Hall. Last but certainly not least, if there are any students joining today, could you please send a chat with your name? We like to track the number of students who are engaging in events. Thanks again very much for joining us, and Beth will kick off the presentation.
Thanks, Kristen. I'd also like to share that Sam Han Duville and James DeSoto from CTS are also on the call supporting the webinar today. So here's a description of what we're going to talk about. Understanding how infrastructure materials perform over time is critical to making informed design, construction, and maintenance decisions. This webinar will feature 2 recent research efforts that examine the real-world performance of commonly used transportation infrastructure materials. Brock Hedegaard is here to share insights from his recently completed research project on the causes of concrete culvert pipe joint separation, highlighting factors that influence concrete pipe performance and long-term reliability. Michael Pluimer will present findings from a study that evaluated corrugated HDPE pipes manufactured with recycled content, including how recycled materials perform in transportation infrastructure applications and considerations for their use. Together, these presentations will provide a practical look at how material selection, manufacturing, and construction practices affect infrastructure performance. So I'm pleased to welcome today's speakers. Brock Hedegaard is an associate professor of civil engineering at the University of Minnesota Duluth and is a CTS scholar. Mike Pluimer is the director of the Advanced Materials Center and an associate professor of civil engineering at the University of Minnesota Duluth. So I'm going to turn it over to Brock.
There we go. All right, so let me share my screen here and we will get started. I have a few buttons to push though. A few more buttons to push, it turns out. Okay, now we're almost ready. Apologize for the delay. Share. Excellent. I think we're good to go then. So welcome everybody. I am Professor Brock Hedegaard from the University of Minnesota Duluth. I'll be talking today on understanding causes of concrete culvert pipe joint separation. This was a project that we just recently finished collaborating with Minnesota Department of Transportation. On the screen, you can see some of my colleagues that helped with this work. So Professor Carlos Carranza Torres, also at the University of Minnesota Duluth, our graduate student that did a lot of the research as part of this is Mady Faley, and he just recently graduated in December. And then Dr. Ben Diamond was also consulting with this project, and he is from Northern Arizona University. All right, so let's dive right in, just talking about a little bit of the motivation for where this research came from and why the Minnesota DOT wanted us to look into this problem. So um, approximately 75% of highway culverts owned by the state of Minnesota are concrete pipes. So it's the vast majority of the Minnesota inventory. And among these pipes, the most common distress that we see is joint separation. So roughly 20% of the inventory has some sort of joint separation. And how MnDOT defines joint separation in this context is when we install a pipe, usually we have an allowable gap in that joint of 1 inch or less. So if we have a gap of greater than 1 inch, then that would be classified as joint separation. So again, that affects about 20% of the inventory. Some of the issues that can happen when you have joint separation is that you can have infiltration, which would be soil coming in through the pipe, into the pipe through the joints, and that can lead to either loss of soil support, failure of the pipe, clogging of the pipe, so a number of issues related to that. So the goal of this research was to find out what the primary causes of joint separation are and to propose construction or maintenance practices to help control this issue. We can see on the right here, I hope you can see my mouse there, and if not, it's on the right. The just a typical installation for this. This is a arch pipe actually, so it's slightly different from most of the pipes throughout the state. Almost all pipes throughout the state are actually round pipe, but we can see this is a very recent installation. The pipe ties are installed on the outside. They are steel bars that extend from one pipe segment to the other. And wherever you see this geotextile wrap, there is going to be a joint at that particular location. So that's going to be the focus of our discussion today. So typical current practices for these concrete pipes is we'll focus on, again, pipes that have either ties or no ties. So there's actually quite a few different details throughout the state, and especially in terms of the historical record on how these pipes were installed and what actually crosses that joint there. So on the upper left here, we see a single tie connection. This is sort of an L bar or an angle bar that's anchored in on both sides of the joint. And nominally, this is to help prevent that joint from opening up. Per the details, this is not supposed to be used to sort of tighten the joints together. Sometimes out in the field, that is unavoidable. But yeah, the point of this is essentially just to make sure that there's some sort of load transfer across that joint. Most pipes will have two of these, one at the 2 o'clock position and one at the 10 o'clock position throughout the pipe. Very large pipes may have more, and many pipes will have some of these on every joint, but that's not necessarily the case. So older pipes or some other like storm sewer culverts, for example, may have no joint ties at all. So there's completely untied joints, while some pipes will have only the apron tied on, so only at the end, or perhaps only the first one or two joints being tied. So we'll see pipe ties pretty often, both in the field, and then they'll be discussed throughout this research as well. The most common types of joints we have among our concrete pipes is the bell and spigot one. So these two on the left, A and B, are two different types of bell and spigot joints that we'll see. Or we have tongue and groove joints, often sealed with some sort of mastic right there. And that would be C and D would be our tongue and groove joints. And we can see on the upper right here, just a photo of a couple pipe segments before they are being put into place. This is a bell and spigot type joint. You can see how it flares out at the end. Most of the time, these culvert segments are about 8 feet long. And yeah, there'll be a joint about every 8 feet along the length of your pipe. So when we talk about joint separation, we're talking about opening of the joint. And specifically, it's a measurement of the current state of that joint. So, for example, here on the left, we have a 3-inch separation. This is, as part of this research, we did get to go out in the field and inspect a bunch of these culverts. So I can actually reach my hand into there. That is my hand, I guess. I can reach my hand through there, and I can touch soil on the other side of this joint. So that one is completely open. Presumably there was no geotextile wrap on this one. It's hard to inspect that after the fact once it's in the ground, but the fact that I could touch soil was a little bit disconcerting. This would be a much smaller and almost more typical case that we see, just a small 2-inch separation. This wouldn't usually be flagged as anything concerning. You can see that this one also has some pipe ties on the exterior based on the bolts that are coming through the side of the pipe wall there. In very extreme cases, we see very large separations. So this one is about 6 to 7 inches of separation. And then we've also noticed that there's breakage of the joint. And through our field inspections, we realize that that's a very common correlation where if you have separations, it's pretty common that you'll also have breakage of the joint. So unfortunately, as part of the project, it was difficult to assess whether that breakage happened, for example, during construction, because many of these pipes are quite old. And because of that breakage, that led to more joint separation, or if it happens the other way around, where if you have a large amount of joint separation, and then forces get transferred to that joint in a way that they weren't intended to, and then you get a breakage afterwards. So it's hard to tell from, again, the historical record, but as a general rule, breakage of joints often is correlated with this wide separation. So again, that leads to a greatly reduced condition rating for a lot of these culverts that have large separations. And again, as I mentioned, a lot of or many of the problems that arise from joint separation is not just the fact that the joint happens to be open. If there's not a lot of infiltration, it may not lead to anything critical or concerning. But there are plenty of pipes out there that do have infiltration issues if they have a joint opening. So here's just a couple examples where, for example, we see some separation and infiltration at all joints. That would be quite likely if there's no geotextile wrap on the outside, because the separation of these joints is actually quite small. So we wouldn't expect to get normally infiltration at every single joint here. There are extreme cases. This pipe was recently, or not recently, but it was repaired previously on one joint, and then the next joint had a failure as well, and it's just piling up with junk. Or you'll have large separations along the whole length with infiltration effectively everywhere. So that's just a scope of sort of the process and the problem that we're dealing with here. And so what we were tasked to do was to look into the primary causes for why these pipes separate and to hopefully come up with some answers for what we can do about that. And so our research approach, we had a sort of three-pronged approach to this. The first one was just a database investigation. So the state of Minnesota maintains what's called the TAMS Hide Infra database, and that has a listing of all their culverts with condition and specifications, inspection records, everything like that. So we wanted to examine that database to find any commonalities of pipes that have joint separation. Approach two was field surveys, so that we went out in the summer and we did a bunch of inspections. I'm not going to talk about that one too much. For the most part, that was sort of supporting what we were doing with approaches 1 and 3, which I just noticed is objective 3. That's wrong. That's okay. So many of the photos and other insights that we got from our field surveys are just going to be integrated into the discussion for the database and our computational models. So approach 3 was, again, the computational models. We modeled soil culvert systems. We were looking at essentially parametric modeling, so modeling a wide variety of different systems to try to investigate things such as live loading, so vehicles above of the pipes, settlement, freeze thaw, things like that. So this talk will focus on approaches 1 and 3, and for field surveys, I'll just sometimes throw in an extra comment here and there. So let's begin with the database investigation. So first, from the database, we wanted to see what is the scope of joint separation in the recorded inventory here. And so you can see here we have a plot where the x-axis here is the length of our pipe. So L is the length of the pipe. That's the total length, broken up into categories from 25 feet all the way up to 300 feet long pipe. The blue bar is the total number of pipes in that particular category. So we can see most pipes are going to be 25 to 75 feet long. And I should note these are all round pipes under highways. So that would be a typical, say, 2-lane highway pipe would be generally in that range with lower fill depth. So if you have a very high fill depth, it starts to get longer. So most of your pipes are going to be between 50 and 100 feet in length. The orange bar here is the number of those pipes that have joint separation, and then the red line shows that percentage. So, for example, we see most separation in this 50 to 75 feet long pipes. So 21.9% of the pipes in that category would have joint separation. So overall, it works out to be about 20% of the concrete pipe inventory that has some form of joint separation. And again, when this gets flagged as joint separation, that means there's an opening in at least one joint that's greater than 1 inch. How long that joint opening has been there is up to debate. We don't necessarily know that. The other thing that we don't necessarily know is if that is actually deleterious to the pipe. In a lot of these cases, many of these pipes with small joint opening would be classified as having separation, but have no issues. However, we did want to see what that correlates to in terms of the overall condition of the pipes. So once again, similar idea, the blue is going to be the count of each bin. And so this is based on the condition number that's given to those pipes in that database. 0 being unknown, 1 being a like new pipe, and then 4 being the worst case, a severe pipe. And to no surprise, pipes that have a low condition rating, or technically a poor condition rating, poor or severe, are going to have a very high incidence of joint separation. So whether or not, again, this means that pipes that are in low condition will then separate, or if separation leads to low condition, we don't have a causal statement for that. But what we can say is that if there are pipes that are getting degraded down to that level, it's very likely that joint separation is involved. We also wanted to look at the geographic distribution of this by county throughout the state. So you can see on the right, we have a plot of the state of Minnesota, and the darker the color in general, the more percentage of the pipes, concrete pipes in that county have joint separation. So for example, you can see a couple concentrations of separation. There's a few right here in central Minnesota, but most of them are going to be actually down in the south part of the state. So for example, in the south east region, so in the driftless area down here, we have quite a bit of separation down there. And then also over on the southwest side. One thing that a lot of these locations have in common is that they have rapidly changing geomorphology. So driftless region in particular in the southeast corner of the state, there's no like glacial scour or glacial drift that went through that region. So it has a very sort of hilly and erosion kind of based geomorphology. So we found that in general, locations with that kind of geomorphology had considerably more joint separation, which leads credence to an idea that it is a strongly soil dependent type of motion here. So if you have soil that is not very erosion resistant, for example, then it's much more likely that you may have joint separations. We also wanted to look at the effectiveness of pipe ties. So a couple caveats about how pipe ties are recorded in the database. As a general rule, pipe ties are either a yes or no answer within the HyDinfo database, and so that makes it a little bit tricky. Um, so among the yes categories, we inspected all of the comments on those, and some of them would have comments saying that uh, clarified how many pipe ties there were. Not all of them, though. So in this plot, full ties is a bit of a misnomer here. So the bars on the left, when we say full ties, really what we mean is that there was a yes in the database that it had pipe ties, but there was no other comment that said, well, the pipe ties are only on, for example, the apron or only on the first three joints. So that really should be full ties or otherwise unknown condition of pipe ties. There were 579 entries where comments indicated that pipe ties were not placed on every joint. So we called that partial ties. And for cases like that, that would be, for example, only the apron being tied or only the three joints at the end being tied. And then no ties, obviously that one is pretty self-explanatory. The database said there was no ties for those. So we looked at that percentage of joint separation in each of those categories, and we found that the partial ties actually had by far the most joint separation, which we found kind of interesting. About 38% of those pipes had partial ties. Now, there could be some bias to that result because, um, for example, it might have been commented on that there were only pipe ties on a couple joints because somebody saw joint separation and wanted to clarify, for example, like why such and such a joint was separating, even though it had pipe ties. But even then, we still see having no ties is sometimes effective. Full ties is obviously much more effective. But we did want to look into that in a little bit more detail. So that partial tie condition will bring back up later when we did some of our modeling to see if there was any kind of truth to this. And it turns out that partial tie, this procedure of partial ties, which again, historically was quite common, may actually lead to more joint separation. So we'll come back to that when we talk about the models. So we also wanted to look at the effective pipe diameter. Overall, bigger pipes tended to have a little bit more joint separation, but it wasn't a major concern. Overall, very small pipes really don't have a lot of separation, so that is um, promising. But pretty much if you have a 24-inch pipe or greater, um, there's not a lot of variation in your separation by your pipe diameter. However, with soil cover, this makes a very big difference, and a very clear trend emerged from the database where we saw that higher amounts of cover almost universally led to higher rates of joint separation in those pipes. So if we have very large amounts of cover over 16 feet, those pipes would have over 30%, or over 30%, excuse me, of those pipes had joint separation, and that ratcheted up. I don't want to say linearly because the scale in the x-axis is not doesn't make any sense, but it as that depth of cover increases, that does actually increase your joint separation. Again, we found that quite interesting, so we wanted to investigate that in a little bit more detail in our models to figure out why that might be the case. So that brings us to our computational modeling, and let's talk about what we did for our modeling. So technically, we did two different types of models, but for today's webinar, I only want to focus on one type. So we did some finite difference modeling using Itasca, so FLAC 3D software. That was sort of a base case model that we investigated some rather simple cases. So we preferred to use finite element model for really everything else. So this slide gives you a scope of how much modeling that we did. So here is our embankment for our roadway, and then we have culvert segments just going through that. So we modeled half of the roadway here, as you can see. So the line on the back side of this would be like the center line of the road. And then there's boundary conditions on the sides here to mimic the fact that obviously the road will keep continuing in the direction. So traffic would go across this sort of from like southwest to northeast in that direction, for example. Um, we looked at three different subgrade reactions. So at the base of this model, there is a spring support, essentially, that's going to model the soil beneath that. And so we had a poor, good, and excellent subgrade to model different types of soil stiffness below our culvert. And then we had two different soil modulus values for the embankment itself. So we had a low stiffness embankment and a high stiffness embankment, different by a factor of 10. And then these values are taken roughly from guidance from MnDOT geotech folks, and then also just a general feel for ranges of the materials for example, like silty sand up to a well-compacted base. So we would anticipate that most embankments throughout the state are going to be a high stiffness, to be perfectly honest. But we did want to look at, well, what if that has a poorly consolidated or a much less stiff embankment? We looked at three different values of cover for our models: 4 foot, 6 foot, and 8 foot. So the cover we're talking about is the amount of soil from the top of the culvert up to the top of the embankment there. As your cover increases, we have to make the pipe longer just because then our slope goes out further. So there's a differing number of segments for each of these models as well. We looked at two different pipe diameters, either a 24-inch or a 72-inch. Because of the database results, we didn't anticipate we'd see much differences between pipe diameters. We expect to see more differences between the cover depths there. And finally, we looked at two different styles of modeling overall. So to try to model the different types of joints. So we did a continuous or tied pipe model or a discrete untied model. So for a continuous model, all the pipe segments are bonded together. So it effectively acts as one long continuous segment. That's going to be a bit more constraint than would be achieved by, for example, just two pipe ties. But in general, those segments now are unable to separate as a general rule. In those models, we wanted to look at how much force was being transferred across that joint. In the discrete model case, each of the joints is untied, so they are capable of separating, and therefore we can't measure a force across that joint. So instead, what we measured was the opening of that joint under some specific loading in our model. So for example, we'll be looking at how much that joint opens under the self-weight of the embankment, under the weight of a vehicle on the driving surface, and so on. The last thing that I'll comment on this is that the modeling and the field don't perfectly line up, as you'll notice. So in the field, we look at a condition of a pipe and we say it has joint separation if there's currently more than 1 inch of separation. Well, our model doesn't give us a current condition. It will give us a change in a joint opening or how much that moves under a specific action, whether that's self-weight or if it's a truckload. So at best, these can point us in the direction for where we would expect to have problems and what variables are pushing you in what direction. But it's unlikely that these numbers are going to be hard and fast rules. So if, for example, you're to say, I want to design my pipe ties to carry whatever load is on here, it's unlikely that your pipe is actually experiencing that level of load. There's a number of assumptions that go into these models that make it a bit conservative. So it's an overestimate, but there's not an easy way of classifying how much conservatism you have in that estimate. So take that with a grain of salt. What we're looking for is sort of directionally, does this open the pipe? Does it close it? How much? Which of these actions are more important and less important? So diving into some of the results, we'll start with the continuous pipe. So the continuous pipe, again, is tied together so we can transfer force across the joints. And what we're looking at here for our results, the x-axis is going to be the length of our pipe. So x equals 0 is the center line of the road. And 40, or the end of this, 56, is the end of the pipe where it emerges from your embankment. Each of the dots represents a joint. So every 8 feet, we're assuming we have a segment. And the y-axis here is the axial force that develops in that particular joint. So the axial force is going to be a force that pulls that segment apart. And then this can be effectively directly read from the model. So the results that we're looking at here are under the self-weight of the embankment and the pipe itself. So essentially, this would be a locked-in amount of force after construction of this pipe. So the full embankment has been built on top of it, and now we're seeing how much force is acting through that pipe. And what we'll notice again is that, and I think this is probably obvious, the axial force in the pipe is going to be roughly proportional to the amount of cover that you have. If we want to be very precise, it's roughly proportional to the depth to the center line of your pipe, which is slightly different because it changes for pipe diameters. But that level of proportionality holds actually pretty well for most levels of cover. So the more cover you have, the more force that's sort of just built into every one of those joints. The fact that this axial force is positive means that is tensile. So that means it is pulling it apart. So under the self-weight of the embankment, that embankment has a tendency of deflecting outwards when you push it down. And that overall force is actually going to separate pretty much all your segments along the whole length, where you get the largest amount of, I'll call it separation potential, in the middle of the embankment, obviously, because that's where you have the largest amount of self-weight. It turns out for dead weight, just the self weight, your subgrade does not matter actually that much, because most of what the force is the stiffness of the soil kind of moving out. But the embankment stiffness does matter. So if I have a low stiffness of my embankment, my forces are almost twice as much as if I have a well-consolidated effective embankment of, for example, like 29 KSI stiffness. The only time the subgrade really matters is if you have a effective embankment already. So if you have an effective embankment, the subgrade is sort of a secondary factor. But if your embankment soil is poor, the subgrade doesn't really matter already. You may already have problems actually if your embankment is poor. If we look at traffic loading, so this would be a design tandem, so that would be a 50 kip load placed on the roadway surface. Technically, in our model, we put two of these on the road, so one in each lane effectively. So they're adjacent to each other on each half of the model, if you will. And so once again, we're looking at axial force in each of those joints. The first thing that we'll notice is that this design load presents far less axial force than what you see just under even normal cover depths. So 4 to 8 feet of cover, which again, that's what we see in the majority of our pipes, has 5 perhaps times more axial force going through your segments. So just due to dead weight. So compared to just dead load, traffic load is actually a pretty minor player in terms of joint separation. As we'd expect, most of the joints or most of the demand is going to be happening in the segments right under the road, which makes sense. That's where your load is. Subgrade does not matter a whole lot unless you have an effective stiffness of your soil. But you'll notice that the difference between a low stiffness soil and a high stiffness soil is not very strong when we're looking at traffic loading. In general, it's not really a very big player in terms of separation potential. So we wanted to look at those same results in our discrete joint model. So again, this one, we can't transfer force across the joint. So we look at a joint opening under that load. First thing that we'll notice is that this joint opening is very small. So our y-axis is now joint opening, and these are on the order of fractions of inches. One thing to keep in mind is that this model is elastic soil. So if you have plasticity or other kind of sliding mechanisms, we could anticipate this to be greater than that. So once again, we're kind of looking at directionally what's going on here. But the other thing that I'll comment on these slides is that if you look at the y-axis here for the low stiffness soils, the ones on the left, compared to the ones on the right, we'll notice that this y-axis is much smaller. It only goes up to 0.015, really peaking at a much smaller number. It's less than a hundredth of an inch according to our model. Whereas with the low stiffness, you have much greater openings. So once again, we see that the stiffness of your embankment is an extremely important factor for how much separation that you have. It's probably the most driving factor. So if you have poor embankment soils, that can hurt you, whereas the subgrade only starts to matter if your embankment is already effective. And then looking at traffic load in a similar kind of way, we see the low stiffness soil and the high stiffness soil have very different openings just based on the y-axis there. When we're no longer able to transfer force across that pipe, we see that you'll get a opening just below the load, and actually the pipes that are close to the end will be compressed together. So the load effectively attempts to compress the segments that are close to the edge, which also we would expect for these kinds of pipes. So where things get a little bit more interesting is if we look at something like soil freezing. So for a soil freezing model, we took the top 6 feet of an embankment. So this is this particular picture has 8 feet of cover, and we froze 6 feet deep. Now that's pretty extreme, but we do see that in northern Minnesota. So we did look at some like soil depth or frost depth records to get those numbers. If you're down in the south end of the state, it might be closer to the 4 or 3 feet, depending on where you're at. But we wanted to look at a pretty extreme case here. So this goes to 6 feet deep. But our soil expansion is quite low, so 0.0125. That would be typical for a well-graded, good embankment soil, we'll say. And if we look at our joint opening under this, if we have either a high or low stiffness soil, we can see that, as you'd expect, because most of the soil expansion for freezing is happening out at the end, that we're going to have the largest amounts of joint separation out at the end. And this magnitude of joint separation, 0.015, is considerably bigger than what we saw from traffic loads. So it's highly likely that this would more strongly encourage joint separation, especially if you have a frost heave susceptible soil. So depending on how these are installed, some of these systems are installed with a cohesive soil cap, essentially to like the top, say 2 or 3 feet, could be like a soil material to prevent water going through that. So sometimes that's encouraged when they're installing these pipes. So if you have a clay type soil, some kind of cohesive soil cap, those might have actually a fairly high amount of expansion under freezing, even up to 1%. So if you have a 1% expansion out by the surface, this 0.015 inches of opening can suddenly balloon up to 1.3 inches. And that starts to look like what we are expecting for joint separation in the field, is where we see several inches of separation. How could this come about? It's like the most likely answer is very large soil movements. So either expansion or large amounts of settlement. That's really the main causes that could drive this. So again, very large soil movements, you could get up to 1 inch of separation or more. So with that led us to some of our. Oh, I have one more thing to say on this before I get to the conclusions. So with soil freezing, because there is that common detail where it's like, hey, let's tie the first 3 joints. So for this particular model, we tied 3 of the joints and then left the rest of them untied. So by tying them, it just means we fixed them. So this is sort of a mix between our continuous pipe model and our discrete joint model. So we got 4 continuous segments here that are all tied together and 1 untied joint. As we can see in the results down below, even though that untied joint is past the frost depth, you'll find that the total motion of that embankment pulls all 4 of those units of culvert, or all those lengths of culvert, out together, and it concentrates your separation in one particular location. So it turns out tying some of the pipe tie, or providing some pipe ties, actually gives you larger joint separations than if you just had left them all untied. So this actually leads some credence to the results that we saw in the database, where we saw partially tied pipes were more likely to have joint separation. And from these kind of results, we can see that that may very well be the case, because now we're taking what would be maybe a small amount of separation in four different joints and concentrating it all into the first untied joint, just past that frost depth. So now I can get to the modeling conclusions. So in terms of self-weight versus traffic loading, the embankment weight applies separation everywhere. Um, and even for just a modest 4 feet of cover, self-weight causes 2 to 4 times more opening than we see from traffic. So in general, traffic, like I said, is probably a minor player in these. If we look at the effect of the embankment stiffness, this is by far the most critical factor. So if you have a low stiffness embankment, you are probably going to have joint problems. And then soil freezing was the really the only action that we looked at that could have orders of magnitude on like inches of separation at those joints. So that was our most likely cause, that or just other large soil movements. So overall conclusions of this project, pipe damage was quite often correlated with what we saw in our field inspections. So again, maybe that's an installation error, or it happens after the fact. It's impossible to tell. But as a general rule, pipe separation or joint separation does seem highly correlated with a degradation of these pipes. In terms of the self-weight demands and installation, this is far exceeds your live load demands in general, especially for large cover depths. So that also can lead credence to why we see higher cover pipes being more at risk for joint separation, is because the weight of that embankment is separating the whole system, and there's just more built up tension in that type of system. So there's more likelihood that you'll have a separation. And then again, soil freezing is going to be our most likely cause for direct separation at the ends. And I'll also mention, because I think I forgot to do that, when we were looking at our field inspections and also in terms of talking with the MnDOT inspectors, most of the time we see separations at the apron or at the first joint in after the apron, or like we saw with our model, at the first untied joint if you have only, for example, 3 joints tied. That was by far the most common situation that we saw. And so that also lines up with our modeling expectations with soil freezing. So recommendations for installation, we really should be tying all joints. So I know this is actually pretty common now. Most modern pipes are tied everywhere, but it lends a lot of support to why we do this. Tying only three joints at the ends has, from this research, it looks like it actually causes more problems than it helps. Bedding material and compaction. The bedding material maybe doesn't matter so much, but you do want a solid embankment stiffness, so that should be well compacted. And it should also be resistant to freezing. So we shouldn't be using soils that have large amounts of expansion under freezing. So that idea of having a cohesive soil cap might actually be problematic. There are other reasons that we use that. For example, when we're installing it and there's a lot of water going through, it's nice to sort of dam that off. But we just have to keep in mind that that is putting more demand on those joints, because now you have more expansion at the ends. And then there's possibilities for other alternative apron designs. We haven't really talked about this in this presentation, and that's not something that we looked into in a whole lot of detail, but MnDOT was kind of interested in looking into that further. Are there other apron designs that can help cap the pipe ends so that it doesn't keep deflecting out? So that's recommended for further research. And that wraps up this presentation. Oh my goodness, that was very long. Sorry, Dr. Pluimer. And yeah, I guess we'll move on to the next one.
Brock, thank you very much. We're going to turn it over to Michael, and then we'll handle questions at the end for both presentations.
Excellent. So let me end my share screen here, and then we'll turn it over.
Thank you.
Oops, that button doesn't do it. There we go.
All right, Michael, it's all yours.
Okay, can you all see my full screen now?
Yep.
Okay, great. It would help if I could though. Okay,
We can actually see your whole presentation, not just one slide.
let's see if I can change that. Uh, Let me try this one more time. I had this earlier, but now it's not working for me. Hold on. Better?
There you go.
Okay. Sorry for the delay there, and I'll try to get us caught up a little bit here. Thank you so much, Dr. Hedegaard, for your great presentation. Appreciate it. And now we're going to look at a different pipe material. This is going to be related to corrugated high-density polyethylene pipes. And so what we'd like to do was go over a recent research project that we conducted with MnDOT for these types of products. And what I'm going to do is do a brief introduction of our research team first, and then give some background information for the what really prompted this research, why MnDOT was interested in this. And so we'll talk about some other research that have been conducted. Then we'll talk about what we actually did with MnDOT and give some conclusions and some questions. So the research team involved myself. I've got a PhD from Villanova University, and the topic for my dissertation was actually studying pipes manufactured with recycled content. So this is really relevant to some of my area of research. I'm currently an associate professor in the civil engineering department at University of Minnesota Duluth, and also the director of our Advanced Materials Center. Uh, Katie Patton and Masa Salimi were graduate students that worked with me on this project. They have both since graduated, Katie in civil engineering and Masa was in applied material science and engineering. Corrugated high-density polyethylene pipes are used for storm drainage, culvert applications, and they conform to various standards, both within ASTM and AASHTO. The prior to the previous research that was conducted, the highway standards in AASHTO required these products to be manufactured with 100% virgin materials. And so around 2018, actually the research started prior to that, around 2011 actually, research was started to investigate the use of recycled materials for these pipes from an environmental benefit standpoint as well as a cost standpoint. And that research ultimately resulted in 2018 of an update to the M294 standard to allow these types of materials, recycled materials, to be used for these pipes for manufacturing for highway applications. There were three broad research projects that supported that change to incorporate recycled materials, and they were two NCHRP projects. NCHRP stands for National Cooperative Highway Research Program. And so these were about nearly $1 million worth of research. Texas Research International was the principal investigator of the first project, and then I was the principal investigator of the second project, which studied was more of a field study of the performance of pipes manufactured with recycled materials. And then another funder of this project was the Southeastern Pennsylvania Transit Authority, and they sponsored my PhD dissertation work with Villanova University. SEPTA was interested in using pipes manufactured with recycled materials as a more sustainable alternative underneath their rail applications. And so that's why they approached us for this project as well. So that is the supporting research that I'm going to briefly discuss first, and then we'll go into what we did with MnDOT. So before we get started, some of the supporting research, we had to define some terms. So what do we mean by recycled materials? There's two broad categories of recycled materials: post-industrial and post-consumer. Post-industrial recycled materials are now typically referred to as pre-consumer materials because these are materials that really have never reached an end user. So these are products, maybe a material that was manufacturing a product that didn't meet specification for whatever reason. They could then reuse that product, cut the material up, chop it up into pellets again, and reuse it. If it had never reached an end user before, it is now termed a post-industrial recycled material. So these could be reject parts and things like that. A couple images on the upper right there show these materials that have been chopped and formed into pellets or flakes. And then in the upper right-hand corner, that's a typical conduit pipe, for example. So if those pipes were manufactured and did not meet specification for whatever reason, they could be sold to somebody else to chop them up and use them as a post-industrial recycled material, for example. But more commonly, when we think of recycled materials for pipe applications, we're dealing mostly with post-consumer recycled materials. And these are those materials that you might be very familiar with. These are your milk bottles, maybe. These are your Tide laundry detergent bottles, other things like that that you put in your recycling bin. And the polyethylene materials can be sorted from those plastics and then reused and reincorporated into piping applications. So on the lower left-hand corner, we see an image of a typical post-consumer recycled flake material that has gone through a recycling facility, been washed and chopped into these flakes. And then what the pipe manufacturers will do is they will repelletize those materials, as shown in the lower right-hand corner, and then they become recycled materials that are available for manufacturing purposes. Why would we be interested in this? Well, this graphic from the Plastics Pipe Institute actually, I think, does a really good job of summarizing some of the issues that are out there. So typically those Tide bottles, those milk bottles that you're thinking of putting into your recycling bin, we get lots of questions. Where do they go? Many people say, well, they end up in the landfill. And unfortunately, that happens a lot of times, a lot more often than we would like, that those materials end up in places we don't want them, and often could eventually pollute our rivers and streams and lakes, and nobody likes that. And those bottles, that milk bottle, for example, or that Tide bottle, might have a service life of 6 months to a year or something, that it's going to sit on a shelf and then get consumed and then thrown into that recycling bin. So the idea is, what if we can take that material? The negative about plastics is that, well, they persist for a long, long time. They just don't go away. Well, that's a very positive attribute when we're talking about piping systems, where we want them to last a long time. So what if we took that bottle out of that blue tub, that recycling bin, and we converted it into a pellet that goes into a plastic pipe that's going to service that community, or that serve as a storm drain into that community underneath that very same curb for up to 100 years. That's the concept. And I think it really certainly resonates with my students, and I think the general public as well. And we've seen some really good reasons to do this. The big question is, how do we do this responsibly, such that we don't impact or adversely affect the service life of these pipes? And to better understand that, we need to know the primary failure mechanisms that we're concerned with for high density polyethylene materials. So there's typically what we refer to as 3 stages of failure. Stage 1 are ductile failures, which occur at very high stresses and low time durations. So this is a graph of log of stress on the y-axis and log of time on the x-axis. And then stage 2 failures are brittle failures. This is typically referred to as slow crack growth. These occur at moderate stresses, low to moderate stresses over long, long periods of time. And then stage 3 failures are chemical failures, or just a chemical breakdown of the material, such as oxidation or UV degradation or something like that. For drainage pipes that we're talking about for this presentation, we're not really concerned with stage 1 ductile failures, because the stresses inside these gravity flow pipes are not at that range that we're going to get ductile failures. But we are concerned with preventing stage 2 and stage 3 failures. And so the idea of this research was to make sure that those failure curves are pushed out far enough to the right that they will exceed 100 years of service. So to do this, we actually had to invent a new test method called the unnotched constant ligament stress test. And this is testing materials for their stress crack resistance relative to the different contaminants and different materials that might be in that material. So for example, for a virgin material, there might not be a real likelihood that you're going to have a contaminant, but that likelihood could be increased if we're incorporating recycled materials. So we invented a new test method to test the effects of those contaminants on the stress cracking mechanism, and then we tied that test method to service life. We did that by conducting this test in elevated temperatures and elevated stresses, and then correlating that to service temperatures and service stresses. This is a very typical practice in the geosynthetics and plastics industry, where we can use the principles of Arrhenius to test at elevated temperature conditions and then extrapolate the data to service conditions that might be more appropriate for your given application. Two of the most common methods are called the Poplar shift method and the rate process method. For the purposes of this presentation, I'll focus on the Poplar shift and just show you how this is done. So basically, we require the testing to be conducted at multiple temperature stress conditions. Condition 1 is at 80 degrees C and 650 psi stress, for example. Condition 2 at 80 degrees C and 450 psi. Condition 3 at 70 and 650. And then we apply these shift factors to those failed data points at each of these conditions to get what we call a master curve, which is a prediction or a projection of how how long it would take these materials to fail in that brittle crack stress mechanism under various stresses at different temperatures. So in this case, we're shifting the data to 23 degrees C, which is about ambient temperature. It's actually a little bit warmer than what we would see pipes in Minnesota buried at, but it is maybe a temperature that we'd see a pipe in Florida buried at. If we're at colder temperatures, this curve would shift even further to the right. So this is a pretty conservative model that we're using at 23 degrees C. So based off of that model, then we could do this test for any different material with any blend of recycled content and predict how long that pipe would last at various stress conditions. 500 psi is a very conservative assumption for the buried stress in a plastic drainage pipe. It assumes a fairly high deflected pipe and a condition that we typically don't see at stress levels at this level. But it's a number that's been used traditionally in the plastic pipe industry, especially in the case of Florida Department of Transportation in their 100-year service life model. So that's why we select 500 for our data point there. And the previous research, then what we did is we developed the model, and then we validated that model in some extreme installation conditions to see if it played out in real life. And what we found is that the model perfectly fit the pipes that we tested. So we had multiple full-scale pipes that were tested. In the upper right-hand corner, you can see a simulated burial chamber where we simulated 100 feet of fill on a pipe that was installed in that concrete chamber. And then we also did a number of tests in the lab and some field testing as well to validate the model. And the end result ended up being a number of publications. And one of the things that I think was really beneficial was this Astral publication, which is a standard recommended practice for determining the service life of corrugated pipes manufactured with recycled content. This would allow any pipe manufacturer or any state DOT to take a sample of their pipe material, assuming it has recycled content in it, and predict how long that material will last in that given installation. So even pipes that are poorly installed or have an excessive deflection, we can then correlate the service life of that product given the material properties. Some of the changes that went into M294 to changes, we basically have two categories now of pipes in there. M294V represents pipes manufactured with virgin materials, and M294R represents pipes manufactured with recycled content. You can see that the material requirements are the same for both of those. Both meet cell class 435400C. Stress crack resistance, accordance to the NCLS test method, is the same for both. We do require a 20-minute OIT requirement for the pipes manufactured with recycled content, and that's some added assurance that there will not be that there's enough antioxidants in that material to protect it and stabilize it against oxidation. And then we have an elongation of break test that's required on the recycled materials, and as we mentioned earlier, a 34-hour UCLS test requirement, which is the equivalent or ensures a 100-year service at 23 degrees C. So with that as background, I'm going to go quickly into what we covered for the Minnesota Department of Transportation. So MnDOT was interested in using pipes manufactured with recycled materials as a more sustainable alternative. And so we wanted to do a test with them and study the performance of these pipes in those conditions. And what we did was decided to base our study with MnDOT on some previous research that we did for SEPTA and with that NCHRP project, where we basically installed pipes, some manufactured with recycled materials, some with virgin materials, in the same trench underneath, in our case, we did a road. In this case, it was underneath a railroad. But for MnDOT, we did underneath a road. And we identified several different benefits of this for MnDOT as part of the project. Increased potential construction savings, engineering and administrative costs, certainly some environmental potential benefits and improved life cycle costs, and then the technology benefits with regards to a new method for service life analysis of these products. So we procured about 140 feet of pipe from Advanced Drainage Systems. 80 feet of that was manufactured with virgin materials and 60 feet with recycled materials. This was all 36-inch diameter pipes. And we instrumented them with strain gauge and potentiometers. Here's a few images of our instrumentation. And again, I'm going a little bit quick here because I know we're getting short on time. But we'll be happy to address any questions afterwards or follow up with anybody if they would like to see some more details of this. Pipes were then, they were instrumented at our University of Minnesota Duluth facility and then loaded onto a truck to be hauled to the test site where they were installed. And that test site was in Fosston, Minnesota, which is up on the northwest corner there. You can see it's kind of over by Bemidji. And there was a 24-inch diameter reinforced concrete pipe culvert that we were going to replace with these pipes. That culvert was a little bit undersized, and it was also failing at the joints, which is kind of appropriate for in accordance with Brock's previous presentation. Not a lot of cover, about 5 feet of cover from the top of the pipe to the bottom of the road. And as you can see in the lower image there, we were alternating pipes, a virgin pipe followed by a recycled pipe all the way throughout the run of the system. We had compacted materials to about 10 inches above the top of the pipe, and then we used select granular backfill above that before the pavement. This is also addressing one of Brock's points that he brought up earlier with regards to joint separation. This isn't really for joint separation, but in this case, we wanted to wrap that trench with a geotextile fabric to keep infiltration of the native materials from going into the backfill material. So this is just showing some images of that. And we installed piped underneath the eastbound lanes first, and those pipes were not instrumented with any sensors because we were only recording sensing traffic loading on the westbound lane. So this is the eastbound lane was constructed first. Showing a few images of the construction process, you can see some knifing of the backfill materials. I was not supervising this particular installation, and the contractors in this area weren't, frankly, real familiar with plastic pipe installation. So there were a few things, mistakes that I think were made along the way. One, the lift height was greater than what it should have been. Generally, we like to compact these things in 12-inch or less lifts, and they use greater than that. So there was some compaction issues in the pipes as it was being installed. That said, I think it was still a good test for this specific case, just because it was really going to push the limits of the material. We inspected the joint gaps after installation. So you can see these are very, very small joint gaps. Corrugated high-density polyethylene pipes and polypropylene pipes, for that matter, can have a fairly large joint separation and still perform well. The joint design is quite a bit different than that in concrete pipes. But typically we like to make sure that these pipes are homed at installation, and these were all installed very well from a joint standpoint. We then did the westbound lanes, and in this case, we had to make sure our sensors were lined up appropriately with the traffic loading. Then we recorded some deflections both pre and after installation, and you can see our deflections were reasonable there, a little bit greater on the virgin pipe than the recycled pipe, showing 3 to 4.5% of deflection after construction. This was before the final pavement. And the same thing on the recycled pipe was about 1 to 2.5%. And then we went into our situation of monitoring these pipes and seeing how they were performing. And as shown in the images here, there was quite a bit of difficulty in doing that. The pipe was always flowing full. And again, I had graduate students working on this project with a limited time to go collect data. So we were not really successful in getting data collected with regards to live loads due to the difficulty in entering these pipes and the high water loads. You can see on the picture on the right there, I have a student going into the pipe there, which really wasn't that great of a condition to be collecting data. I give her a lot of credit for going in there, but this was the end of our inspections on these just because there was not a good way without dewatering the pipes, which is really what we're going to do next on this, is to do a complete dewatering and full inspection of them. That said, she was able to gather some data, both horizontal and vertical deflection measurements due to the sediment in the pipes and the how much material was in these and flowing through these pipes. It was very difficult to get accurate vertical and horizontal deflection measurements. So the measurements here should be taken with a little bit of a grain of salt or a grain of sand or backfill material, if you will. But in this case, we're seeing greater deflections than we would have liked with the virgin pipe, especially the recycled pipe was performing pretty well, but still, again, a little bit greater deflection than we would have liked. But the horizontal deflections were reasonable. The vertical were a little bit greater than we wanted. Again, I'm not confident of those deflection measurements though, given the sediment that was in the bottom of the pipe. So we're planning on going back into these pipes and dewatering them and doing a complete investigation once we get MnDOT's blessing to do so. The pipe material testing, we tested both pipes, the virgin pipe as well as the recycled pipe, for all of the material properties. And you can see the material performance was very, very close between these two pipes. If you look, for example, at the yield strength of the material, both over 4,000 psi yield strength, the flexural modulus, very, very close. And then from a stress crack resistant standpoint, they both performed well also. And the UCLS test requirements, we typically require 34 hours for that test on recycled materials, and we were over 159 hours on this particular pipe. Then we also did a literature review to do an analysis, a life cycle analysis, to determine the environmental benefits, the potential environmental benefits of pipes manufactured with recycled content over other materials. So in this, we have 5 different categories that were evaluated by Franklin Associates. This is a published independent study that was done on different piping materials. And we're comparing polyethylene in the blue bar with polyethylene with 50% recycled content with the red bar, PVC with the orange, reinforced concrete pipe in the purple, and then steel, aluminized steel with in the light blue. And you can see in many of these categories, the pipes manufactured with 50% recycled content perform better than the other materials. And this is a scale that was published, kind of a ranking showing that the pipe in bold there on the 4th column, manufactured with 50% post-consumer recycled material, was the best performer related to global warming potential, acidification, et cetera, in the majority of these 5 categories. We also wanted to quantify the cost benefits of using this, because one of the motivations for using pipes manufactured with recycled content is cost. And so we followed the standard LCCA life cycle cost analysis methodology. Every major pipe industry has their own standard practice for life cycle cost analysis, and they all involve some type of equation similar to equation 1 there, where we put the present value life cycle cost, we factor in the initial cost, the operating and maintenance costs, and then the residual costs. So we did an overall analysis and showed some benefits in using pipes manufactured with recycled materials over competing materials, with typically 30+% savings with that product over some of the other materials. That's in the lower right-hand corner. You can see our overall cost per year estimate on that product. And again, this is going to vary by region. It's going to vary with regards to different parameters. These were some of the costs that were local to this particular area, but it might be different in different areas. But generally speaking, we can see some cost savings by using pipes manufactured with recycled content. I will say that pipes manufactured with virgin materials aren't always more expensive than recycled materials, and it does fluctuate. And but it is a good reason to use recycled materials because, for example, right now we're in a case of resin prices might be going up, not so much in the United States, but in some of the other countries due to the conflict over in Iran. And so that can affect virgin price materials pretty quickly. And so maybe it makes recycled materials more attractive from a cost standpoint. So they're just having, I think, a different material streams available is going to be beneficial. And so, just in conclusion, the M294R pipes perform comparably. I would say maybe slightly better than the M294V pipes for this specific application. And we hadn't seen any change in performance since the installation. We're going to go back out again, like I said, and dewater these pipes and do a closer inspection. But I think that so far everything is performing in accordance as we would expect. And both the LCA and LCCA showed some benefits in using pipes manufactured with recycled content. And that UCLS test is a great test to allow us to actually predict the service life of these pipes. With that, I'd like to thank MnDOT for sponsoring the project, and a special thanks to Eric Brenna and David Glyer and Rachel Miller, who were very involved and engaged in the project throughout, and for managing this project, and then also the MnDOT Technical Advisory Committee for their review. And I know I went pretty quickly, but I was trying to get us caught up a little bit on time here. So thank you for your time and attention. And with that, we will, I believe, turn it back over to the moderators.
Yes, thank you, Michael. Thank you both, Brock and Michael, for your presentations. Lots of really great content. I'm going to have Kristen facilitate the Q&A. I think we do have some questions here.
Yes, thanks everyone. I see a few attendees popped online after the introduction. So just as a reminder, if you are looking for PDH certificates or AICP maintenance credit certificates, please put your name and your email address in the chat and we'll follow up with you after today's meeting. Also, if you are a student, please drop your name in the chat because we are tracking student attendance for these webinars as well. Would anybody like to get started with a raise hand question? So if you raise your hand, we will unmute you. Okay, hearing no questions, maybe to get...
We've got Graham with his hand up.
Oh, I'm sorry, I missed that one. Sam, could you unmute Graham? Thanks, Beth. Go ahead, Graham.
You should be unmuted. Are you able? We can't hear anything.
We'll go ahead to some of the questions online for those who have been chatting in the chat on the side. First of all, I'll start with, are there generally more joint movements in the field in the north part of our state? Dr. Hedegaard, did you want to expand on that from the chat?
I would say in general, no. So, yeah, most of the joint separations that we observed, particularly from the database, actually do happen in the southern part of the state. So, that seems to imply that maybe the actual depth of frost is not the important factor that drives the separation. So, it's much more likely that the amount of separation that you have in that soil is just going to be much more important. It's possible also you're going to have more freeze thaw cycles down in the south, because you get more, we'll call them false springs, opposed to up north. And that may also have a factor because it's highly likely when it thaws and expands, it does not contract again, once it goes into the spring. So then that could be driving further opening. So yeah, we have been seeing more separation actually in the south rather than the north.
Interesting.
Another question from the chat box. Could the RCP pipe joint separation models be adapted to look at plastic pipe joints? Would the researchers expect more or less separation potential for plastic pipe?
Yeah, I'm happy to address that one, and maybe Brock can weigh in as well.
Yep, we can both present some comments on that, I think.
Yeah, I mean, I do think that it could be applied. Certainly, that the model would be slightly different because the material properties are different. The weights and stuff might be different, but the soil weight would be the same, and the principles would be the same. As I alluded to in my discussion, the criteria for joint gaps are different in plastic pipes versus concrete pipes, just because the bell and spigot joint on a plastic pipe is different design than the joint on a reinforced concrete pipe. And so it's a little bit different criteria there that would have to be incorporated. And then I think the other significant difference might be the fact that the corrugated plastic pipes typically have a corrugated exterior that interlocks with the soils. Would be interesting to see how the model would apply to that. Because on one hand, you're going to have a little bit more engagement of the soil with the pipe. Maybe it's going to, have a little bit more force pulling things apart. I will say in the field, we haven't seen joint separation as a significant issue in plastic pipes. It's a little bit more of a forgiving design, but I do think it's the model. I'd be very interested in trying to apply it. So, Brock, I'll turn it over to you to see if you agree or disagree with that one, I guess.
Oh, I think I do agree. All the loads that get transferred to the pipes in these separation issues is always mediated through the soil in some kind of way. So that interface between the soil and the actual pipe itself is going to be one of the most important factors. And I mean, in a lot of ways, that soil demand is going to be the same regardless of what your pipe material is looking like. So whether or not it results in more separation in a plastic pipe versus a concrete pipe, I don't really know. I think that, like Michael said, there are going to be different criteria for what a sort of joint failure and looks like, even for those two pipes. Um, yeah, and I don't know. So how exactly, and maybe you can talk about this a little bit more, Michael, like how are the joints fixed together in the plastic pipes compared to how we do it in concrete pipes?
Yeah. Good question. So it's similar to concrete pipe that there's a bell and spigot design. I mean, you talked about the tongue and groove design as well, but a bell and spigot. But the biggest difference is that the overlap of that bell going over the spigot is significantly longer. So you've got maybe 3 or 4 inches of potential for that joint to move before you get any soil leakage through that. Now, the industry doesn't recommend a 3-inch joint gap there, but again, there's a lot more room for movement. And then the other thing is, since it is a flexible pipe, it typically conforms a little bit more with the soil as well. So we just haven't seen that joint separation is common in these pipes. And then the other difference is that there's oftentimes a double gasket that's used in plastic pipe industry for putting those pipes together to give further joint performance. So it'd be interesting though. It'd be really interesting to apply the model and see how it would perform on plastic pipes.
I
Another
agree.
question.
Oh,
As another question, was the alignment of the pipe investigated at all during the course of the joint separation investigation? Were joint gaps uniform or variable around the circumference of the pipe?
I will say that joint gaps are actually quite uniform, which surprised me. A lot of the historical research on this idea had been looking at, for example, live loads on pipes. And as a general rule, when you put the live load on there, it will get it puts a moment on there, so it rotates. So you would get generally more separation on one side of the pipe and less separation on the other side of the pipe. But what we see in a lot of the pipes out in the field is actually there's just the pipe just opens So if we have, for example, 2 inches of separation, that's 2 inches of separation generally around the whole circumference. So when I list variables, like where there was one of the pipes in the presentation where I said it had 6 to 7 inches of separation, that would be, for example, the difference. So if it separates 6 inches at the top and 7 inches at the bottom, there is a differential there, but overall that is a relatively uniform opening. So that was one of the main things that kind of led us to how we wanted to look at our model too, is rather than specifically looking at flexural demands in pipes, looking at how much they actually get pulled apart. Um, but yeah, so we were quite surprised by that too.
Thank you very much for that. One last question, and we're still watching for hands online. If you want to raise your hand and speak your question aloud, we'll unmute you. Going back to the photo of the highway culvert in District 2, was that for a stream crossing?
Sorry about that. It was not for a stream crossing, but in essence, it was turned into a stream crossing. It was a very, very low wetland area that was flowing pretty significantly there. So I don't think it was identified as an official stream, but it was functioning as one. So there was a very, very low wetland there that was draining from one side to the other.
Okay, thank you. We might have time for one more question. We'll give it another minute and then we'll hand it back to Beth for the wrap up. All right, Beth, you want to walk us through the round robin?
Yes, I will do that. Thank you, Kristen. And thank you again to our speakers and great questions, everybody. So we have a round robin session now. Just like to ask everyone on the call here today a few questions and just open things up to further discussion. So the questions are: what current infrastructure issues are you or your organization facing? Do you have any organizational, informational, or event updates to share? And what ideas do you have for potential future council meeting topics or speakers? So open it up for folks, anybody to answer any of those three questions. And you can raise your hand and we'll unmute you. While we're waiting, I'll just put in a plug for the American Public Works Association. They have their annual spring conference coming up on May 6th through the 8th. And it's up in Brainerd at Grandview Lodge. And it's a great networking event with a lot of local practitioners and across the state, folks in the public and private sector that do public works things. I'll put the link to the conference in the chat. Yes, this is information here that I would definitely agree with. Nicholas said that this would be good information to share at the Water Resources Conference. I'm not sure if you guys are maybe lined up for that, but I believe that's still a fall conference every year. He's saying abstracts are due May 29th for that conference.
Thanks for that note, Nicholas. I'm not currently registered or wasn't planning on that, but it might be a good one to look into. So thank you.
And it looks like that's October 13th to the 14th.
Thank you, Brock.
But that'll be fun down in St. Paul.
Anybody else have things to share with the group?
Well, I am from the Brainerd area, so do you know if the APWA conference is going to include golf? Because we have a great golf area up at Grandview. So I'm assuming there must be golf out there.
Yes, I think there's an unofficial golf outing both Wednesday and Thursday for part of the day. So yeah, we're
Great.
always hoping for good weather, but sometimes we get it and sometimes we don't.
I'll try to order some for you.
Thank you. All right. Doesn't sound like anybody has any pressing issues they'd like to bring up for the group. So just one more thank you for Michael and Brock for their presentation today. And keep an eye out for the future presentations that Kristen mentioned. We've got some great content coming up and some in-person events. So thanks again for everyone for their attendance.
Thanks, everyone.
Thank
Bye-bye.
you.